I think there may be a theory which is a linkage between the very small and the very large, which gives us a deeper understanding into the forces of nature, the size of the universe, and the kind of particles and atoms that exist in the universe. I think there will be that. But once we have that theory, that's not the end of science, it's the end of one phase. Most of what we see in the universe, including the particles, can be explained as space and time being wrapped up in very complicated ways. And one interesting complication, which is a feature of all these ideas, is extra dimensions beyond the ones we're used to. We're used to the three dimensions of space, left and right, up and down, forwards and backwards.
Yeah, there are four.
And time
is four.
Yes.
Yeah. And some people even say there are 6 and 7 dimensions.
Well, indeed, and there may well be. And many people suspect that there are extra dimensions which we don't see because they're wrapped up on tiny scales. Many people believe that space itself has a grainy structure, just like any substance like this chair has, but whereas the grainy structure of material objects is on a scale of atoms, the grainy structure of space is on a scale a trillion times smaller than atoms. That's why it's so hard to get any relevant experiments. But the suspicion is that on that tiny scale, space has a complicated structure where there may be extra dimensions which we don't see because they're rolled up very tightly. And the analogy people give here is if you have a hose pipe, which is really three-dimensional, it looks like a line from a large distance, and likewise there may be these extra dimensions. But there's an even more exciting idea which relates to brains, which is that perhaps some of these dimensions aren't completely rolled up. There is even the idea that there may be other universes, as it were, apart from ours, and there may, for instance, be another universe which is only a millimetre away from ours, but we can't detect it because that millimetre is measured in some extra spatial dimension and we're imprisoned in our 3. Just like if you imagine a whole lot of bugs crawling around on a big sheet of paper, which they think of as their two-dimensional universe, there might be another set of bugs on a parallel sheet of paper thinking that they were in a separate universe, and if they had no concept of the third dimension, they couldn't be aware of the other. So we've got this amazing emergent process starting from this hot, dense beginning and leading up to the universe we are part of. But the very beginning is still shrouded in mystery. As we extrapolate back closer and closer to time equals 0, as it were, then everything gets hotter and hotter, denser and denser. And when we get back into the first tiny fraction of a second, the first microsecond, the problem is that the conditions become more extreme than anything we can simulate here on Earth in our labs, and so things become more uncertain. So from a microsecond onwards, I would say that what a cosmologist tells you about the universe should be taken as seriously as what a geophysicist tells you about the universe.
And there'd be a consensus about that?
I think there would be a consensus.
After the first?
Not universal, but a very broad consensus about after the first microsecond was up. But when we go back earlier still, then the basic physics is still very uncertain, and that makes things more conjectural, more speculative, but on the other hand more exciting, because the only way we may understand and test alternative theories for the extreme conditions that prevail then is by very careful and subtle observations of the universe.
If you collected 10 of the wisest people you know in your field, is there one big question that they most would want to answer, and would there be a consensus on that question?
I think there would be consensus that mysteries lie in the very early stages of our universe, and we won't be able to answer those until we have this unified theory, unifying quantum theory and gravity. They would agree on that. I don't think it'd be quite a consensus, but I'll tell you what would be my main question, which I think many string theorists would agree, and that is the question of how large is physical reality. What I mean by this is there's this huge volume we can see with our telescopes extending about 10 billion years, the aftermath of our Big Bang. But is that all there is? There could be a lot more beyond our horizon that our telescopes can't detect because the light hasn't time to get to us. There might even be other space-times separated from us in an extra dimension, or many other Big Bangs. And so many people believe that there's a lot more to physical reality than the cosmic patch, as it were, the volume of space and time, which we can observe with our telescopes. And this leads to a separate question. We know that the laws of physics are the same everywhere we can see with our telescopes. If I look at a distant galaxy and look at its light and take a spectrum of that light, the atoms there are the same as the atoms in the lab. But it could be that there are other domains, other Big Bangs, that lead to cosmoses governed by quite different laws of nature, where gravity is much stronger, where there are different numbers of dimensions, etc. So physical reality may be much richer than a part of space and time we can see. And the key question is whether we will ever have a theory of the kind where we can write it on our t-shirt, which will tell us formally for the strength of gravity, the mass of the electron, and things like that.
Yes, what you said was there's a question as to whether we will ever have that.
Will we ever have that, yes. And the reason we may never have it is it could be that there is a theory, but it applies to a deeper level. And what we think of as fundamental are really environmental accidents, local bylaws in our cosmic patch. Let me give you an analogy. Think about snowflakes. Snowflakes all have hexagonal symmetry, and we understand why that's the case. It's a fundamental feature of the water molecule. But every snowflake is different, and it's different because the way it grows depends in detail on the actual humidity and temperature in the rain cloud where it forms. So for a snowflake, there's a basic symmetry that they all have, and then there are environmental features. Now what we don't yet know is whether what we call the laws of nature are all bedrock features, or whether some of them may be environmental accidents, rather like the details of a snowflake, and the environmental accidents will be properties of our own Big Bang. So we will be in a region 10 billion years across which cool down in a particular way and ends up governed by particular laws. But that may still be just a tiny patch compared to the entire cosmos. So the answer to that question, whether the laws of nature are unique, is very important, because it may require us to take our cosmic modesty one stage further. We've gone from the stage where the cosmos was our solar system plus the vault of heaven, to when it was our galaxy, and to when it was our universe of zillions of galaxies. But it could be that our Big Bang is just one of many Big Bangs, and we have a still grander scale.